All right, thank you. Okay, just a quick intro. I'm Yousif Hussin. I'm a security engineer at Google. I very recently switched teams within Google, and currently I'm in a team called Enterprise Infrastructure Protection. And it's basically the team that is responsible for building security controls for Google's infrastructure. And that was very recent. And up to the point of changing teams, I was actually working in another team called Vulnerability Coordination Center. And what I'm going to be talking about here is more relevant to my past role. And I'm going to go through some story of an engagement that I led, of a response to an identification of a vulnerability, which I did when I was in my previous team. So, Yousif Hussin, the team that I was in is the Vulnerability Coordination Center, and that team, the core responsibility of this team is to lead the remediation to supercritical, big, large-scale vulnerabilities that affect Google products. As you probably can imagine, sometimes addressing vulnerabilities is not as simple as just push a button and update. Sometimes it might involve a lot of people, a lot of teams, a lot of systems. And getting them to fix things sometimes is a little bit more challenging than you would hope. And sometimes it's not really just a technical problem. Sometimes it's got like communication, legal, and documentation, artifact creation. It can get really messy very easy. Imagine if this happens at the scale of Google, it could even be more complex than you can imagine. So this is one of the core roles the team plays. The other team that I'm also part of is the team that responds to the bug bounty researcher reports. So I triage these reports when they come in, when a researcher finds a bug in a Google product, and then I would triage it, learn what it is, reproduce the exploitation of that particular vulnerability, and then work with the developers on how to fix it. Now, the bug bounty part isn't necessarily involving critical, complex vulnerabilities that need somebody from the Vulnerability Coordination Center to lead. But sometimes there is an escalation path that happens from this bug bounty program to the Vulnerability Coordination Center when we find something super interesting. Because I'm part of both teams, I'm the only one at Google that actually does both. Sometimes I would be sitting on in the bug bounty side, and I would find something that I triaged, which seemed a little bit maybe small, and then I find out that, oh, well, this is actually pretty big. And then I would escalate it to the Vulnerability Coordination Center, to this other person, really good person named Yousif, that would take the response to that vulnerability and lead it. So I would escalate it to myself, and I would basically do here and there. How do we do that? The Vulnerability Coordination Center team is an interesting team because you really have to be pretty good at a lot of things. And that includes like leadership, working with other teams in terms of like the technical capabilities and how you can roll out things. But at the same time, taking into account all of the different complexities that surround fixing vulnerabilities. Now that I introduced myself, I wanted to introduce this person. I tend to be a little bit nervous when I do talks like this, especially when I'm surrounded by super smart people like yourselves. And so I thought it might help me to have somebody kind of help me with the presentation in a way. And this is him. His name is Leo. I don't know him. I just got to know him this morning. He might come in throughout the slides 2 or 3 times. And I've heard that he's a good, some people told me he's a good security engineer. Some other people told me he has no idea what he's talking about. Maybe we'll find out throughout the presentation. There's going to be 2 or 3 times I'm going to say something that is so bad and it's just so wrong. Feel free to scream and let me know when I do that. Let's see if somebody can catch it. And feel free to do the same if he says something like that. Disclaimer, this talk is not technical. Oh, I guess I lied. It's a little bit technical. A little bit, not much. How many of you can actually look at something like this and be like, oh, I know what this is. I can read binary just like that. And I can tell you, like, for example, oh, this is a machine instruction for running a hello world program or something like that. Probably not many, but that's fine. I cannot do it. It's very difficult. And the reason I mention this is because I'm going to go through some story about a response, and I just wanted to kind of build the context and just cover a few basics just to make sure that we're on track and we're all on the same page. So as you know, when you write a program and you compile it, and you run it on a machine, it's just a series of bits. That's how the machine runs things. Now, for humans to be able to read these machine instructions, there's like a way to step back from binary a little bit, and you can read something that makes sense, human readable, more human friendly to read, right? And this is probably very familiar to people that work with like malware. So I've been doing incident response, focusing on incident response for the past like 9 years, and I did a little bit of reverse engineering for malware. And sometimes we get to deal with these things where we actually have to read a form of code to be able to tell what the program is doing. So the first time I was looking at binary, and I was like, oh, this is difficult. I won't be able to just look at binary data and be able to tell what that is. And then somebody would tell me, well, don't worry. We can use a tool called the disassembler, and it'll basically tell you this from the binary. I looked at this the first time, and I was like, wow, that didn't help. I was a little embarrassed. I had to, wow, I was surprised, right? Like, okay, but then I just couldn't lie about it. It's like, what the heck is this? So, move, maybe that means move EAX, EBX. What this does is that it turns out that for the machine to perform the calculations and a lot of the operations that it does, it would have to move certain things around. Bits to be moved around between boxes. They're called registers. And to do that, it would have to copy data from one register to the other, and then it will do something with that data. And basically what this particular instruction is basically just a representation of a machine instruction that does a copy from a source to a destination. And in this particular case, it's 2 registers from EBX register to EAX. Okay. Simple, I think. And then there is another instruction that looks a little bit more complex because it's shorter. Because in this case, we have the instruction, but we don't have the operands. We don't have the where is the source and the destination, what, move, but what is it? And the reason for this is because this one, the operands of it are implicit. So when you run an instruction like this, there's a bit of setup that happens in the background that you don't have to worry about, but it's already implied where data is moving from and to. And then there is this rep in front of it, which is really short for repeat. Do it more than once. Okay. So we've got rep move. What happens if I write a machine instruction like this and give it to the machine? Rep move. It's kind of like telling someone, I'm going to do something more than once. I'm going to do something more than once. Kind of doesn't make sense, right? So it turns out what happens is that it would be ignored. It wouldn't cause a problem if you give this to the machine to run it. You do this 2 times, yeah. Same thing, things will go just fine. So that's one concept they just wanted to cover. And there is another. When I was talking about the operands, the registers, EBX and EAX registers, this particular operand has a size. Back in the days, 32-bit registers. 32-bit machines had 8 registers. How many bits do we need to address 8 registers? 3 bits. So that was enough. but then it had 64-bit. How do we address 16 registers with 3 bits in the machine instruction operand? Well, what they did was basically hack it a little bit to make it work. And they were like, well, remember there was this prefix that gets ignored if you add it more than once? Well, that's not going to cause a problem if we add a prefix, but then we can basically just use it to lend us a bit to the 3-bit that we've used previously, and that will end up with like 4 bits, and now we can address 16 registers in the machine. Okay, so that was covered. One more thing I want to cover, ERMS, FSRM. These two are CPU optimization features that were introduced in some of the Intel CPU families. The names are not very friendly. ERMS, FSRM. ERMS, I think, is short for Enhanced Repeat Move Store. FSRM, short for Fast, Short, Repeat, Move. I have no idea why they come up with these names, quite honestly. I mean, I'm pretty sure these are brilliant people. But I can bet like they could have come up with something a little easier. So what they do, what these features do is they're an optimization feature that will basically make the system run a little bit more efficiently when it does certain operations. So I was talking about these repeat operations earlier. These repeat operations need to run in a way that is more efficient, and that's what the CPU will do with you with ERMS. But ERMS had a problem. If the data that you're moving from one source to the destination is under 128 byte, then it's not really worth the investment to do the optimization, because the optimization itself has a little bit of an overhead pre-setup that it will do to make it work. If the data is under that limit, under the 128 byte, then it's really not worth it. But more than that, then it will make the system a little bit more efficient, and that's where FSRM comes in. FSRM is an enhancement to that feature that will basically make it work with data that is under 128 byte. The last concept that I just want to cover, or it's a bit that I want to cover, is this. If anybody knows what this logo is, tell me. Okay. All right, that's enough. I'll get back to this. Thank you. All right, a response to story. So now let's get to the story that I promised I was actually going to tell you. Now that we know what this is, so researchers at Google do a lot of interesting stuff, of course. And one of the things that they do to identify vulnerabilities is some various ways of fuzzing. One of the things that they do sometimes is they would basically get one program, have 2 identical copies of it with certain characteristics that are different, and then they would run it. And if the system behaves differently as a result of one of the programs from the other, then something isn't right. So basically, they would introduce a lot of different conditions, and then they would just randomly fuzz it, then see what the system is going to do. So what happened was, when they were doing the fuzzing, they introduced certain conditions, they added a prefix in a system that has the feature of FSRM, an Intel CPU, with certain conditions, using the prefix on a system that supports FSRM, sometimes it leads to this. By this, I mean a crash. Now, generally, when we talk about a crash, it's bad news, right? But in exploit development and hacking especially, it's pretty good news, especially if you're the person developing the exploits, right? Like, a lot of times, it's actually quite a milestone. You just want to get it to a crash. And that's basically what Reptar was. There's a vulnerability that was identified as a result of this research that causes a denial of service, or causes a crash, causes a machine check exception on a system. So if you give a certain set of machine instructions to the machine, it would crash. So how do we respond to things like this at Google? So first of all, we start with the discovery phase, which is something that we already went through. It was discovered, and this was escalated to the Vulnerability Coordination Center team. And I was assigned to lead the response to this. How are we going to fix this? And let's get it fixed. Initially, you would have something called an embargo period, where nobody talks about this outside, and you just have to go through the process of identifying a fix for this vulnerability and fix things that are critical before we just publish this. And we would have to establish that with the vendor, and in this case was Intel. So we're going to go through certain phases, and I'm going to go through from the start to the end, explaining what we've done. And just to make this a little bit clear, sorry, I just couldn't help it, but I had to add this just to illustrate, okay, we're there. So what do we start doing initially is something called an impact assessment, and we have a standard way of doing that at Google. Oh, we've got a vulnerability. We want to assess the impact. And that basically means what we have to do is, how bad, answers questions like, how bad is it? How can we reproduce it? Is the reproduction of it pretty easy? Can anybody just exploit it if they know the vulnerability? Does it require some setup across network or not? A lot of things like this that we have to understand just to understand the exact risk of this vulnerability. But then we also have to couple that with the products that are affected. So that we can tell, for example, we've got like thousands of machines running in a Google environment that is affected, for example. So that's different from just 5 machines, right? So we've got the impact assessment. The first thing we want to answer is, well, this is causing a crash. Is that really a bad thing? Like, okay, you just caused a crash, right? Like, so I'm just going to say something. Causing a crash isn't really a problem, right? Because you've got your rack, you've got your servers, and you're running things in isolation, and if you just crash, you're crashing your own systems, right? Did somebody say yes? Okay. Well, I mean, in today's world, I mean, we all know, right? You share more than you know, right? Like with others, when it comes to like compute resources, right? Can somebody tell me what comes to mind as a product that could be affected by something like this? What was that? CrowdStrike? Okay. Huh? That's a very good example. In fact, I would say that's the #1 example. But thanks for sharing. So cloud environments, right? Now, okay, so this guy is saying it's no big deal. I guess we kind of disagree with that. So, like I said, cloud. We share things in cloud. And turns out that if you run this, the set of machine instructions on a guest machine, it would cause an MCE machine check exception on the host machine level, which basically means you can just open an account, cloud provider that has a lot of machines that use Intel CPUs. How difficult is that? Pretty easy, right? Just open a VM and then run the instructions, and then you cause a crash on the machine. You don't know who you're sharing it with. It could be with someone very, very important, another customer, and then you cause the machine to crash. So Google Cloud was the #1. We were pretty concerned because we were like, okay, well, Google Cloud is a big product, and we've got a lot of stuff that we have to do. This is how it looks like, basically. It's pretty simple. You've got the Reptar exploit. You run it on an attacker VM. You cause the physical machine to crash, and you end up with crashing other virtual machines that run on the same host machine. I mentioned earlier this Borg. I asked what it is, and somebody said Borg. So a little bit of history. Back in 2000, around 2003, Google thought, OK, we really need to use these machines a little bit more efficiently in general. So we wanted to have an orchestration system that's going to orchestrate how we run software across Google in our data centers globally. And that's where Borg came in. It's basically the system that orchestrates the running of software workloads across our data centers, across all of our clusters globally. So it would do that in containerized systems. And then later on, something became public, and Borg was the origin of it. Something public that does pretty like something very similar to this. Something became public that does something very similar, and I will know about it. Can somebody tell me what that product is? Kubernetes. Exactly. So at Google, we use Borg. Until today, pretty much everything at Google runs on Borg. And like I said, because of the nature of it, containerized environments and machines that are shared, that means, are they affected by a vulnerability like this? I think it is, right? In a similar fashion to cloud. Now, when it comes to systems typically that are affected, do you think that's all? Can somebody tell me a name of something that might be affected? That I didn't mention. OK, we've been talking about servers. Do you think potentially client devices could be affected? So, of course, because some of them also run Intel CPUs. So one of the things that was affected was also Chrome OS devices. But these are client devices, right? So you could crash client devices. In theory, it's very difficult to do. We didn't have a proof of concept for exploiting this in client devices back in the day when this vulnerability was discovered. But in theory, it's possible to do that through a browsing session. But you would end up with crashing the client device. But my friend Leo is saying, no, it's not a big deal. I kind of see his point here, right? Because, you're not really sharing your laptop, right, with someone else most of the times. And if you crash it, yeah, I kind of agree with him. It's just an annoyance, right? You're just going to reboot it. There is an operating system that we all use and love. If it does an update, it will just slap you across the face, and it will do the update, right? And you just have to restart the machine. So it's really not that big a deal. But here is something I want to mention which was important. When the researchers at Google discovered this vulnerability, they were testing and fuzzing on a black box, which is the CPU that we don't really know how things work internally as much. But when we reported this to Intel, they'd be able to do a little bit more. So they looked into this more, and they were like, whoa, interesting. Turns out that with this, you can do privilege escalation. So I think the privilege escalation is a little bit worse than a denial of service or crashing machines. Now, in that frame of thinking, I think you might be able to say, well, now this applies a lot more to client devices, because then if you exploit a client device, you can basically privilege escalate, and then you can own the system. So one of the things we did was do this impact assessment. We have all of these products that we know that they're affected. We have this document called an impact assessment. These are the products. What are the number of the machines that are affected, which basically translates to just a bunch of, I'm sure you all love SQL. And then we would look at these machines, get these numbers, write them down. So now we know how big this is. And then we come to the question of how do we fix it? Now, of course, there is the solution of we can wait for the vendor to fix it. And that could work. That maybe it won't work. But even if it works, there is a risk with this problem because this vulnerability could get leaked. If the vendor takes, like, let's say 2 months, there's like a time frame during which this could get leaked. It could be used by someone. And I'm sure you'd agree that a lot of people would be interested in getting something like this in their hands. So we thought, well, how about we wait for the vendor, Intel, and at the same time, try to develop something of our own. To keep in our back pocket and see how things go. Because somebody came up with an idea. And they said, well, there's a solution. Can anybody tell me what she's trying to say? OK. So he's saying chicken bit. So the chicken bit, it's actually true. There is something called the chicken bit. Sometimes in the CPU, when they introduce a new feature, they would introduce a bit that you can flip, and it will basically disable that feature. I think they named it the chicken bit because if you own a system and you enable that feature, you have the chance to chicken out of the feature. So we could disable that feature that we talked about earlier, the optimization feature, which was a requirement for the exploitation to work. And now you're protected, right? So it works. Can somebody tell me why that would be a problem, given what I've talked about so far? What was that? Well, yeah, that's one way, but I was actually over something else. I was talking about it being a performance feature, right? Yeah. So it affects performance because it is an optimization feature. So when you disable it, performance goes down by about like 10%. Do you think this would be something acceptable, like in an environment like Google, be like, oh, well, GCP, let's just go down 10%. Like, no, it's not going to be that simple. But it is a solution. Like if things go wrong, like really just go south and it just gets leaked, and we really have to do something, it could be an option. We're going to have to pay the tax of going down 10%, and then we're protected against exploiting this vulnerability, right? It's probably better to go down 10% in performance than being hacked, right? So we did actually obtain the fix from the vendor, which is a microcode update to this vulnerability. And then there was a period of testing it. And this testing happens between a few large companies, Google and other similar companies, where we would do the testing on this fix for about months or something like that, or about a month. And then we can basically say, well, that works very well, which means it's likely going to work very well for everyone else. So for server platforms, we've got the fix. And for client platforms, we also got the fix. Now, for server, it's a little bit more complicated because we've got chicken bit and the microcode update, and we have to talk about performance. For clients, it was really easy. We had the update published later, and then it was just applied on client devices. So we can roll out that update to the server platforms. When we tested this, it got to the point where we can say it's PV validated, P validated, production validated, PV, which basically means all these large companies tested it, and now we tell the Intel about it, and then we're ready to publish this at the end of the embargo and share it to everyone. So the server microcode rollout is when we wanted to basically estimate how much time is it going to take to update all the machines at Google that are impacted by this. But then there are a couple of strategies on how we can do that. So we could reboot all the machines and apply the update, like a BIOS update. But I was just talking about performance. Rebooting machines could cause an issue, especially if you're running things on GCP. You might be impacted. I don't think you're going to be happy if we just tell you, hey, we rebooted the machine because there was a security update, and you're running a mission-critical application on it. Then there's the other approach called hot load, which is a mechanism with which you can apply a firmware update without rebooting the machine. And this was tested. It was successful. on a bunch of machines, a big sample at Google, and we were confident enough to go with this. So we went with that updated strategy. On GCP and Borg, pretty much all the affected infrastructure, it was successful and it was transparent. Now, when I say it doesn't have an impact, does it really not have an impact, like 0? I mean, if you're really going to be looking closely at the CPU cycles, or if you have a cockroach into the CPU and looking, yeah, you're going to notice that there is definitely some impact, but it's not the kind of impact that affects an application that runs on that machine. And who does that? Who actually looks that much into this? Like the performance counters and things like that on the CPU to be like, hey, there is a problem. After that, the Chrome OS Fix update was ready. Now, at this point, I talked about a lot of stuff that we've done. And as you might imagine, a lot of these decisions and a lot of this work can be a little bit complex and stressful. And sometimes you might panic. And doing things while you're panicking is a little bit difficult, and it can get a little bit crazy. And you might not actually make the right decisions when you're in panic mode, right? So we have something called IMAG, which is short for Incident Management at Google, and is inspired by protocols that are followed by medics and firefighters, basically. Because if you think about it, we do share pretty much a lot of things when it comes to managing incidents. It's a set of protocols on how you can manage incidents at Google, including things like building a team for that incident, creating communication channels, and a process on how you can lead the incident end-to-end. So you'd build a team, and that was the team. That's me. The best team ever, right? I can imagine, a lot of you would relate. If you just do everything by yourself, it would be just easy, right? It's simple. You don't actually have to tell anybody else to do anything. But in reality, that's not actually the way it works. So I would be the incident commander, following the IMAG protocols. I remember when I joined Google, there was a mandatory training for IMAG. This is how you do IMAG. I remember, so the way it works is that when you create a team with IMAG, you become kind of like the CEO within that incident. And then you would be basically responsible for it. It's basically the only time they say you'd be able to boss your own boss, because your boss might be part of the response and you'd be their boss. So I'd be the incident commander, and then, of course, the first person that comes to mind would be someone called the operations lead, because I need people to start fixing things, do the operations stuff. Of course, under operations, the operations lead is not going to do everything by himself, so he's going to have to get somebody to lead data center mitigation. And everybody that I'm mentioning here is a lead. Under each lead, there is another team and a lot of individuals under that lead. So in this case, we've had data center response lead, and then cloud response lead, and the person that's actually going to work on mitigating cloud environments. And on the other side, we've got somebody who's going to be leading mitigation for Chrome OS responses. Corporate systems response lead and platform security lead, these are responsible for the corporate side, like internal infrastructure. There is the tech research lead, and this person is the lead of the team that actually does the research and the ones that identified the vulnerability. We have a tech lead who also does the engagement with Intel, with the vendor. Communication lead, of course, because we have to create communication artifacts. When we're communicating with other Googlers, other people at Google, or people external about this, we have to do this in a certain way, so we need somebody to lead that. So internal, external, and we needed somebody to lead how we're going to be communicating with GCP customers. And of course, there's the legal lead that actually takes care of things around legal approvals of how we're communicating things. So this is how the team looks like in general. And then this orange one is a little interesting. So this is alphabet companies that are not Google, because you also have to fix things there. We had a lead that was going to be leading mitigation in that side. So we got to this point, we've addressed everything, we had a team, and everything was successful. Of course, the last bit would be to publish this. So everything is fixed, we're fine. Now we can tell everybody about it because everybody else needs to also fix their stuff. So there's disclosure date. And it's the day basically we wait for. It's been like 3 months, being stressed out about this response, and we've done it, right? Okay, we're happy. So we published it, and when we published this, we published it in a publication called the Security Bulletin, I'm sure a lot of you know about. And then we also published a tool called Icebreak, so that anybody would be able to just run that tool in their environment and be able to tell if their environment is vulnerable to this, or their machine is vulnerable to this vulnerability. And then later on, somebody sent us this message. If you were the incident commander, would you be concerned? I was just about to go on holiday. So we did investigate this a little bit. We started running the Icebreak tool ourselves in our environments and stuff, and we went to the people that developed the Icebreak tool to look into this a little bit more, and turns out there was a bug in the Icebreak tool. So the tool that will tell you whether you're vulnerable or not had a little bug in it, so it was lying. So that was good news. It was a scare, but things were fine. What did we learn from this response? As you've already seen, when we had this vulnerability, we dealt with it like a traditional response, just like you've got hacked, even though we haven't. And that's how we do it at Google. When we have a vulnerability of this scale, be like, well, we already have a problem, and we can follow the same set of protocols and how we can manage an incident in general. What did we learn? Well, one of the things that we learned was that following IMAC protocols was really, really necessary. It really did help a lot. What can we do better? It's always better to automate things so you don't actually have to do things by hand or on the fly during an incident. And it's very difficult to do this. We still did a little bit of let's just do this now for the first time kind of stuff during the incident. So maybe some of this could have been better if we could get to a point where we don't actually have to do things on the fly, and you already know what you're doing, and you just follow a playbook. It's very difficult to get to that point where we can say everything is just on a playbook. But that's one thing we could improve. Can we automate? Definitely. We have a lot of great automations at Google, but there's always a way you can make things a little bit better. Are we prepared for the next one? I did change teams, so it's their problem now. But no, I'm just kidding. I mean, I do believe that generally, I would say Google is prepared for this. Now, one of the things I worked on, when I was introducing myself, I didn't mention, one of the things I've been doing also is developing security tools for security teams. So I love building automations. And one of the things that I built at Google, for example, was ingesting a lot of intelligence data from different sources, and then dynamically adjust bugs that we have internal at Google about vulnerabilities. If there is an exploit to it that became public, then automatically you basically just raise the alarm and basically just modify the severity of certain vulnerabilities that we have identified internally and work with it in a prioritized fashion, and sometimes automatically respond to these vulnerabilities. So I did develop that automation. One of the things that I thought I could also develop is something that helps us when we respond to large vulnerabilities, like CPU vulnerabilities. And one of the things that was challenging was doing things that you feel like, well, why am I doing this by hand? And one of them is creating artifacts, like the security bulletin, communication documentations, preparing a reactive statement just in case of something goes on gets leaked or something like that, in case something gets leaked. So I thought we could automate some of this work, also including things like preparing the fixes and linking that to the automation systems that basically push the fixes. A lot of this. So I thought we could automate this, so I worked on a project where I actually did start working on an automation platform that would automate a big portion of this. And this would basically create a process. What I did was I created a process that is very well streamlined for responding to CPU vulnerabilities, so that when the incident commander is leading a response to a vulnerability like this, they don't have to worry about a lot of it, or thinking how we can do things. You don't have to think about that. Just focus on the response and how you can do a lot of the details and how you can follow the process and how you do the response. You don't have to worry much about that. Just do what you're prescribed. And it's driven by this automation and the artifacts that are created by this automation. And last thing I want to mention, if you want to connect with me, I'm more than happy to be connected with in LinkedIn. And that's my email, which I think is pretty easy, blackhat@google.com. And I hope you enjoyed this presentation, and it kind of gives you an insight of how we do responses to large-scale vulnerabilities at Google. Thank you. So, any questions?
I saw one hand up there. Okay, I think he was first, so give me just a second.
Just a disclaimer. I might be able to answer the question directly. If not, I might ask you to chat over lunch.
Hi, João. I'm just curious if it was considered or not before receiving a new microcode from Intel, especially for the GCP case, which is, let's say, the risk one, to develop some mitigation on the VM level, so far the hypervisor.
So the problem with this is that it's a bit of a unique kind of vulnerability. And this is similar to the question that sometimes I get about how do we detect this? Can you use like some logs that you can get at the operating system level or something on the network level? And the problem is it's very, very difficult with these kind of vulnerabilities because it's very, very low level. It's at the CPU level. You can try to do things at a higher level, but chances are they're not going to work very well because it's a very low level vulnerability. So it's one of those things that I'll probably just say it has to be fixed with a microcode update that you'd get from the vendor most of the times, or disable a feature like the chicken bit that I just mentioned. Even for detection, by the way, like one of the challenges we had was how do we detect this if somebody's exploiting this right now? One of the ways that we thought about was performance counters of the CPU. Now, if you want to do this at scale, like Google, it's difficult, but you could come up with things like this, but it's really challenging. And then the other thing is, let's say that you're SSHing into a machine across the internet, and you're running these instructions. On a network level, how are you going to detect something like this? So you see, these are some of the things that we get, which is kind of similar to what you just mentioned about mitigations. It's a very low-level kind of problem. It's difficult to do anything about it at a higher level than that. I hope that answers it.
Anyone else?
Hey, thanks for a great talk. I have a question. In your playbook, like you spoke about the chicken bit and how activating chicken bit would grant a performance hit. Do you have like an escape valve? Because, for example, the Spectre and Meltdown and other mitigations have a really big impact on CPU performance. Is there an escape valve in the sense that rather than push for a microcode update where the fix is going to impact performance even more, that you just go, oh, we're just going to go disable this feature and take the performance hit?
Yeah, so are you asking whether we checked how the performance hit looks like.
Yeah, if in your playbook you have a path where the incident lead can just go, oh, we're going to skip a microcode update because the impact is just going to be too big across the board.
Yeah, that's kind of what we did, because we did test it. We tested chicken bit. It wasn't just a theory, we tested it, and the performance hit was about 10%. And we were like, well, that's too big, but let's just keep it in case we don't have any other solution. We might get to a position where we'd be like, you know what, this is leaked or something, and we really need to use that position, use that solution. But for now, we're fine. Let's just wait for the vendor.
All right, awesome.
Any more questions?
Yeah, just one in the front, just last one. We need to then move forward. Sorry.
Okay, thank you. Great talk. I'm kind of curious about something that's not commonly talked about. At least I don't hear it talked about a lot. If I probably understand why, so if you can't answer this, it's okay. But for example, you mentioned that during the, for example, discovery and the treatment of the vulnerability, you had an embargo period during which you could not talk about anything, and there was also, for example, the risk of somebody leaking. For example, did you ever identify or at least suspect there could be a risk of, for example, of an insider threat leaking details about this vulnerability and the exploit?
Yeah, that's a very good question. I didn't talk a lot about, or maybe at all, about, I don't think I talked a lot about the logistics that go internally and how we actually manage this. Now, Google has a very open culture in general, but when we're talking about things like this, we have to be careful, right? So when I was the incident commander for this response, there are certain protocols we have to follow, and whenever we only follow a need-to-know set of protocols. If you don't need to know this because you don't have a significant role in this response, you shouldn't know about this at all. What we do is we use code names. We have a code name for this response, and we refer to it by that code name, and that code name wouldn't help you infer anything about the vulnerability. And then we would only invite a small set of people that are going to be involved in this mitigation, and sometimes some other people would be involved, but they don't know about the vulnerability because they are only asked to do something. Like, for example, if we give you a binary and we say push it to that system, you don't need to know what that is. Just push it, and then you push that system. So yes, so we have to follow this set of protocol, ensuring that only a small group of people know about the details, and only the ones that really need to know about it. How we establish that, there are a lot of mechanisms, as you know. Like, for example, typically what we would do things like creating like an alias or a group that only contains these people, so communication will only use that, and certain meetings that are only going to be involving these people. Communication channels are going to be unique for this response, a different communication channel only for this response, and we're careful about who gets added to that. So these are some of the things we do, if that makes sense.
All right, thank you.
Yeah.
Hey guys, you can catch Yousif outside if you want further questions. We're moving on to the next session. Thank you very much, Yousif.
Thank you, everyone.